board. Okay, so here with this, again, we are not formally tested on this. Do want to reiterate that point for everybody, but this is important information for you to help you next year with calculus and all that. So with trigonometry, we're going to talk about like simplifying things and some trigonometric identities. So our first 6 identities are rather simple. These are what we call our reciprocal identities. So sine is equal to 1 over cosecant. Cosine is equal to 1 over secant. Tangent is equal to 1 over cotangent. Secant is equal to 1 over sine. Cosecant is equal to 1 over sine. I think I accidentally said secant is 1 over sine. Secant is 1 over cosine. And then cotangent is 1 over tangent. How we're going to use these identities, the idea is, we can rewrite, like if I wanted to write sine differently, I'm allowed to write sine as 1 over cosecant if I wish. Sometimes that can be helpful to get things to cancel, things of that nature. Tangent and cotangent do have 2 special ways to write that. We call them our quotient identities. So tangent is equal to sine over cosine. And we'll see a good use of rewriting tangent as sine over cosine in just a little bit. And cotangent can be rewritten as cosine over sine. Now, the Pythagorean theorem happens inside of triangles. If you remember with the unit circle, it was all based on a right triangle. If you recall from the unit circle, our x values were cosine, y values were sine, and then the radius of that circle was 1. The radius happens to be the hypotenuse, sine and cosine are the legs. So what that ends up saying is sine squared plus cosine squared is equal to 1. There are times we may need to solve this to say like, oh, sine squared equals 1 minus cosine squared, or cosine squared equals 1 minus sine squared. There's just a riff on this idea here, but that's a very important identity. So if you have sine squared plus cosine squared of the same value, we know that that's just 1. We know that 1 plus tangent squared is equal to secant squared. We also know that 1 plus cotangent squared is cosecant squared. So these are our big identities. Having these memorized will be helpful. However, I'm going to tell you right now, my calc book in college, literally like reference information like this was the first critical page of hey, here's a bunch of formulas for you that are really helpful as literally just a reference page at the very front of the book. So, having these memorized is great, but a lot of places will give you a cheat sheet for that. So let's see how to deal with this. So our first example here says, explain how to use these trig identities to simplify this. So we're going to go through that. What I want to do here is I am going to say, let's get everything in terms of sine and cosine. If I get things in terms of sine and cosine, maybe some stuff's going to cancel out. Will it? I don't fully know just yet, but that's usually a good place to start with these. These are kind of very hey, did you try this? Did you try that? Type thing. So secant, I know secant is 1 over cosine minus, I know tangent. It's not writing well for me. Let me recalibrate. I start writing tangent. I didn't want to write tangent. I know tangent is sine over cosine, so I'm going to erase, starting to write tangent, and then after I do erase tangent, I'm going to rewrite that as sine over cosine. So that's really sine. Oh, wow, that's still not writing well. Let's try that again. Sine over cosine times the sine of x. Sine over cosine of x times sine of x. Okay, now we're going to keep simplifying from here. When I do this numerator is going to look a little bit interesting here. Just making sure nobody's in the waiting room. Okay. So that actually ends up being equal to 1 over cosine of x. Sine times sine will be sine squared of x over cosine x. Now with how I rewrote this way, all of a sudden I have common denominators of cosine of x. That's actually really handy for me. So what that allows me to now say is, since they're common denominators, I'm allowed to combine the numerators to 1 minus sine squared of x all over cosine x. 1 and sine squared. That's one of our Pythagoreans. It's not how it's formally written out. It's formally written out as sine squared plus cosine squared equals 1. However, if I subtracted sine squared, I know cosine squared is actually equal to 1 minus sine squared. So I can say cosine squared x over cosine squared. If I have a cosine squared over cosine, life's actually pretty easy there. That will actually just reduce to cosine of x. So that original function is actually just cosine of x. Oh, Mr. Osgoff, that was good and fancy and neat what you did there. But does that really equal cosine x? Well, that's what my math says. Let's check it graphically. So that's what example 3 is getting at, is checking it graphically. There we go. So that was secant of x. Then it was minus tangent times sine of x. Minus tangent of x times the sine of x. Well, gee, that sure does look like a cosine curve to me once I type it all in. Let's double check by just typing in cosine of x. And what do you know? The graphs match. This red graph and blue graph are exactly the same. So yes, those are equivalent expressions. Now, this gets to the point of why can it be helpful doing things like this? Well, when you get into calculus, you may get some derivatives or take some integrals to get messy with the trigonometry. And for a brief moment, you might get something like, oh, a secant of x minus tangent times sine of x. It's like, okay, let's work on cleaning that up. And all of a sudden it cleans up to something much nicer. So they're trying to make the claim that secant of x times sine cubed of x plus sine times cosine is equal to tangent. Oh my God. we're not going to do all this here with it. We're just going to check with Desmos. We'll first start with typing this in, and we'll go from there. So let's take out these other two graphs. So that was secant of x times, now I don't think Desmos likes me cubing sine, so I'm going to do sine of x times the sine of x. I'm going to put the second sine of x in a bigger set of parentheses like this, say squared, okay? Desmos is okay with that. But if I put it as a cubed, watch. Oh, it's going to let me do cubed. Cool. I'll do it as a cubed. Before I saw Desmos give me an error when I try and do a sine cubed like that. Then that was the plus sine times cosine. Well, gee, that sure does look like a tangent graph. Let's actually compare it to the tangent of x. And there we go. So yes, those do match up. So actually, I'm going to very quickly kind of go through here how this works. So basically, I can write secant as being over cosine. So I can say the sine of x quantity cubed divided by cosine of x plus, now I want a common denominator of cosine. So I'm actually going to write this out as a sine of x times cosine of x quantity squared, and multiply the denominator by cosine of x. Notice that's still lining up. Once I do that, I could be like, okay, let's combine this as one big fraction to say, and I'm actually going to do a little more rewriting here. The sine of x times a sine of x squared plus this. Still seems to be lining up. I have a common factor of sine, so I'm going to pull that out. So that's going to be the one big fraction bar sine of x times sine squared of x plus cosine squared of x all over cosine of x. Still seems to be lining up. Sine squared plus cosine squared is 1, leaving me with just sine of x divided by the cosine of x. But sine divided by cosine is tangent. So I know that was a little crazy, but if you notice, as I kept writing them, they kept conforming to the tangent. So, that's a way I could kind of use Desmos as a visual. Hey, am I on the right track with this? Now let's quickly change gears and talk about solving trig equations. The big idea with solving trig equations is you get that trig expression by itself. So I want to start with trying to isolate the cosine squared. So I can start, okay, let's add 1 to both sides. That gives me 2 cosine squared of x is equal to 1. Okay, let's divide by 2. And we get the cosine squared of x equals 1/2. However, that's cosine squared. we know from the unit circle, we can determine where cosine's equal to 1/2 off that memorization. However, that's just cosine, not cosine squared. So what I now need to do, let me recalibrate this, is I'm going to take the square root. And taking the square root, we're going to get something we don't recognize right away. But if we rationalize it, we should be able to find that value pretty quick off the unit circle. So cosine of x is equal to square root of 1, just 1, over the square root of 2. Now, I don't like square roots in my denominator, so I'm going to rationalize this by multiplying by root 2 over root 2. So that actually becomes square root of 2 over 2. Ah, we recognize that. By saying the cosine of x is equal to root 2 over 2, we can do the arc sine of everything, or arc cosine, sorry, arc cosine. And thinking back to the unit circle, root 2 over 2, oh, that's at pi over 4. So when I take the arc sine of that, we get that x is equal to pi over 4. So that's the idea of solving a trig problem. Okay, why am I blanking on when class ends? Let me double check my calendar. Yes, over just this one. So, okay, yep, I got time to easily go over one more example. And again, I'll post this recording for you guys too. Not seeing any questions. I know you guys have actually been doing a pretty solid job with a lot of this trig stuff. So, okay, here with this example, the sine's already by itself. So, oh, okay, I'm going to start right away with doing arc sine. So this is where knowing your unit circle comes in really helpful, because I'm going to do the arc sine of the sine of 4x is equal to the arc sine of root 2 over 2. So if I'm looking at the unit circle, again, I've asked you guys to try and memorize it. I have it memorized, so you know, okay, if I'm at pi over, or sorry, I'm looking for root 2 over 2 on the positive part of this. Okay, so that goes, I'm at 0. I go up to here because sine starts at 0, so that's 1/2. Root 2 over 2, that's my second movement. So that puts me at pi over 4 again. So here I have 4x equals pi over 4. So now, oh, I'm just going to divide both sides by 4. Well, I don't like dividing a fraction, so I can multiply by the reciprocal of 4. So that'd be times 1/4. So that gives me x equals pi over 16. And that's it. So that's what I have for you on this kind of like, look, I know this is a fast lesson. I know there's more in-depth stuff to this. I get that. I want to expose you to these ideas so they don't seem totally new and foreign when you had to utilize them inside of calculus next year. You know, This way you can be like, okay, yeah, we did kind of cover that. And whoever's teaching calculus next year, I'm going to make sure they know, yes, we covered trig, but we did not fully cover solving trig equations or simplifying using identities, double angle, angle addition, all that stuff. So we'll do another lesson tomorrow. Again, you don't need to worry about the material itself on there. So stop recording.